Welcome to the Introduction to Energy Management Training, Module 4. In this module, we will discuss electrical energy. Electrical energy can be outlined as electrical circuits, electric motors, electric lighting, and potential opportunities. Let's first discuss the three-phase delta connection. It's connected in a series to form a closed loop where the loads are balanced. A delta connection is generally used in distribution networks since the insulation required is less. Star connection can be used for long distances. Delta connections are used for shorter distances. Delta connections are often used in applications which require a high starting torque. Next, we discuss the three-phase star connection. The main difference being the neutral line within the system. Most induction motors are started directly on line, but when very large motors are started that way, they cause a disturbance of voltage on the supply lines due to the large starting current surges. So to limit the starting current surge, large induction motors are started at reduced voltage and then have full supply voltage reconnected when they run up near the rated speed. This is a reduced voltage starting method. Voltage reduction during star-delta starting is achieved by physically reconfiguring the motor windings as illustrated in the figure. During starting, the motor windings are connected in star configuration as this reduces the voltage across each of the three windings. This also reduces the torque by a factor of 3. After a period of time, for example 5 seconds, it's reconfigured as delta and the motor runs normally. Star-delta starters are probably the most commonly used motor starters in the industry. In this slide, we see a typical load connection for balanced three-phase star connection. We have a line-to-line voltage, we have a line-to-neutral voltage, and we have our amperatures, which is balanced between the three phases. In this slide, we can see the difference between a three-phase motor connected to a delta connection and 3 single-phase motors connected to the delta connection. In the power triangles, we can see the difference between the power triangle for a three-phase motor and the power triangle for a single-phase motor. We can also then see the power triangle for the total load. In this slide is a representational diagram of a delta and star configuration. In a three-phase system, star, you'll notice that the single-phase motors are connected as well as the three-phase motor. The difference being that the lighting circuit is connected between a line and a neutral. The single-phase motors is connected between two lines. It's noteworthy to establish that in three-phase systems, the loads need to be balanced, meaning line 1, 2, and 3, red, white, and blue phases need to be balanced, as this creates a whole lot of power quality issues if unbalanced. Next, we will discuss electrical motors. There are plenty of electrical motors situated in Formosa textiles, so special attention should be paid to this section of the module. Next, let's discuss what is an electric motor. It's an electromechanical device that converts one electrical energy, volts and amperes, into electromotive force, in other words, a magnetic field, to create mechanical rotational energy, resulting in torque and a turning effect. Let's look at the different electric motor types. We have alternating current motors, AC motors, direct current motors, and DC motors, each with their own subcategories. Without a doubt, the standard induction motor, which is a workhorse, is used in most industrial applications. Let's have a look deeper into alternating current motors. The feeder stator with three-phase requirements and set up a rotating magnetic field in the stator. The magnetic field is then induced in the rotor windings, and the rotor then rotates. Moving down into induction motors, the workhorse of the industrial field. Let's have a look a bit at the internal configuration and different parts associated with an induction motor. The main parts being the rotor and the stator. So how does the EMF move the rotor? The rotating magnetic field in a gap produces an EMF. It's a voltage that arises from a conductor moving in a magnetic field. Remember, a two-pole motor has high speed due to less number of poles. Conversely, a four-pole motor has low speed due to more number of poles. This is an effective method of selecting the right choice and speed for electric motor. There might be opportunities where pulley systems and gearboxes, which incur further losses, can totally be taken out of the equation due to just changing the poles of the motor, and thus influencing the rotational speed. Let's now have a look at the wound slip ring motor. This is a different type of, a rotor type. So the rotor is wound with insulated windings. The rotor phase is star connected for three phase. It can improve the starting torque, but it adds resistance to the rotor circuit. The next type is a squirrel cage. It's the simplest, least expensive, and most rugged windings, and it probably accounts for 90% of motors. The rotor is constructed of steel laminations. The windings are conductor bars, usually aluminium, and it's embedded in laminated iron rotor and insulated from core with circuits at end with end rings. So let's look how a squirrel cage induction motor operates. The stator sets up magnetic poles. It's rotating at synchronous speeds. As magnetic field moves past, voltages are induced in squirrel cage inductors. The voltage causes currents to flow in the conductors. The currents largest in conductors under stator poles. The voltage polarity and current direction is opposite under the north and south poles. The rotor currents establish magnetic poles on a rotor. Interaction between a stator and a rotor and the rotor poles produce torque, which gives us our rotation. Induction motor is like a transformer with a rotating secondary. The force that exists between the primary and secondary coils in the transformer now appears in an induction motor as useful torque. Remember, a rotating magnetic field, as in a synchronous motor, also forms the basic operating principle of an asynchronous induction motor. However, instead of the rotor being constructed from permanent magnet material, the induction motor has a rotor constructed only from conductive materials. Let's consider the difference between a three-phase and a single-phase alternating current electric motor. So three-phase is more constant relative to pulsing power in single-phase. It starts and runs better than single-phase motors and employs three balanced voltages, equal in magnitude and differing in phase only by 120 degrees. Three-phase motors are smaller and lighter. Starting of three-phase motors, the motor has low starting resistance and large current will flow on start. Limit the current through starting in star. Reduce the voltage over each phase of the winding. Change to delta to ensure constant voltage supplied to the motor. Induction motor speeds. So speed can be varied by changing the number of poles like previously expressed. For example, 2 poles, 6 poles, 4 poles. changing the frequency of supply. So 50 Hertz, we can supply with 30 Hertz, 40 Hertz, etc. And this all has an influence on the speed of rotation, as displayed in the equation below. In this slide, we have a look at the torque available from an AC motor at different stages, from startup all the way to full load. As you can see, this torque varies, starting, pull-up, breakdown, and full load torque. Most of the torque is thus available at starting and breakdown or pull-out. Let's now have a look at the rotor inductance on torque. Torque is produced assuming pure resistive impedances for the rotor. Impedances are not purely resistive. Significant series inductance. Both the frequency and induced voltage are proportional to slip. Inductance. Current lags behind voltage as slip increases and lag approaches 90 degrees. The effect is that torque is reduced. The stator and rotor poles are lined at zero torque. Let's have a look at this graph again. So as slip is equal to 1 and our slip is equal to 0 on the bottom, the synchronous speed torque is this less than the starting torque. So as soon as slip is 0, the torque becomes lower. Let's now see what happens when we add a VSD to a motor system. On the left we have the full load torque, and at the bottom we have the motor speed. This is varied by changing the frequency supplied to the motor via VSD or VFD, variable frequency drive, or variable speed drive. On a speed from 0 to 100, 100 running at 60 Hz, and 0 likely at 0 Hz. If we run at 35 Hz and our speed is roughly at 50%, our full load torque is within spec at 100%. But if we run it at maximum 60 Hz, our torque is roughly 200 to 300% of full load torque. Let's look at induction motor slip. Let's start with the stator winding. It's connected to the supply. It's circulating a polyphase current equal to a rotating magnetic field. The rotor is magnetic stator field. The magnetic stator field line cuts rotor conductors and induces current, so the rotor follows after the stator field. If it rotates at synchronous speed, no induced current and no torque. This is at a situation where slip is likely 0. The rotor follows at slightly slower speed, so speed decreases with the load. The slip. It's a difference in speed between the flux cutting, the synchronous, and the actual motor speed. So if we look at the designed full load slip, it's the normal RPM subtracted by the full load RPM. The true or actual slip is a no load RPM subtracting the measured RPM. It's important to understand the percentage slip, as this gives an indication on how much a motor is loaded. Let's look at combined curves. We have the load versus the speed. At 5 times full load, the current is quite high, and 60% of full load, the torque. We can see the power factor rising, meaning more useful energy is being used versus being paid for. We want the motors to run between 75 and 90%. That is likely the most efficient place where the most electrical energy is converted into mechanical rotating energy. In this slide, we can see a typical nameplate of a motor and what it all entails. This will be important when replacing an electrical motor, as to replace it with a new higher efficiency motor. We need to know what the motor was doing, and from there we can also right size the motor. We can determine if the motor was oversized or undersized for the application. Let's look at a few typical terminologies that can be seen on a motor nameplate. The kilowatt is a shaft power designed output. The no-load RPM is a synchronous speed. Full load RPM is a running RPM at a designed load. LRA, starting amps. FLA, amps at the designed load. Voltage, maximum capacitor, efficiency, and service factor. Let's now look at a synchronous motor. It uses alternating current to feed the stator. Use direct current to feed the rotor from a separate source. The speed of the rotor is very important in this situation. It is still dependent on the supply frequency and the poles in the stator. Let's look at the characteristics of a synchronous motor. It's usually low speed motor, high horsepower drives, very expensive, and it's got limited applications. The typical application is for compressors. Let's move on to the motor's efficiency classification. To summarize, in the olden days we got EFF 1, 2 and 3 efficiency class motors. That then changed to IE 1, 2, 3, 4 and 5. Keep in mind that using a higher efficiency motor might rotate at a bit higher speed due to more higher efficiency, bearings, etc., and a lot lower losses within the motor. So the motor performance efficiency is a ratio of the output over the input. So it's the mechanical power out over the money that we pay for electrical. At the end of the day, we can also look at it as power mechanical actual out divided by the power electrical in. Above 80 is common at optimum operating conditions. It's an uncontrollable part of efficiency determined by intrinsic losses. For example, your fixed losses, your core losses, friction and rewinding, rotor losses, and stray losses. Your controllable losses, to a certain extent probably, is parts like the load factor. This is a typical nameplate of a Taitong motor, equipment motor at Formosa Textiles. We can see the date of the motor, bearings, rotor, the number of poles, but what we cannot determine from this is what the efficiency class of this motor is. Let's look at a motor on the Summit Alpha machines as well. Again, it's very difficult to determine what efficiency class these motors actually are. Let's delve a bit deeper into motor performance losses, starting with intrinsic losses. This graph explains the efficiency drop off with load reduction. So this means the lower the load of the electrical motor, the lower the efficiency of the electrical motor. We've got fixed losses with the friction, windage and core losses. But our intrinsic losses, I squared R losses, are variable from 0 to 6% and 0 to 2% respectively. Looking at motor efficiency again, we have our energy in and we have our losses and we get our useful energy out. Our energy in IR squared losses usually accounts for about 6%, eddy current losses 2%, hysteresis about 4%, friction losses 1%, and windage losses 1%. And we get out about 84% of the useful 100% energy that we've put into the motor. Looking at the following Sankey diagram of a motor under load. we can see the different types of losses under load. If we have a 20% load, our efficiency is 60%, meaning 60% down from where it should be. 40% load, we lose 25% efficiency, and so forth. The efficiency and power factor versus the load. Again, if we can operate at about 80% of load, we've got no problem. But a lot of motors end up running about 20%, where power factor and efficiency start playing a considerable role, especially power factor. It's worthwhile to note that smaller motors are less sensitive to changes or to percentage rated loads above 100%. However, smaller motors start deteriorating badly in performance losses from 75% down, whereas bigger motors are able to run from about 25% down. Meaning, the smaller the motor, the more emphasis needs to be placed on running the motor on optimal load as to minimize power factor and efficiency losses. Let's again have a look at high efficiency motors and the losses associated. We can introduce low loss steel in the rotor, low loss steel and thin laminations in the core. The stator copper losses, we can use optimum slot full large conductors. Stray losses can be improved by slot geometry. Bearing and fan friction losses is a small cooling fan and better seals. At the end of the day, these are the requirements in order to establish high efficiency motors. Remember, power of an electric motor is equal to 2 pi Nt, meaning if torque increases or if the RPMs increase, power will ultimately increase. Let's have a look at standard and high efficiency motors, a difference between the two at the percentages of loads. You can see that the high efficiency motor is always more efficient no matter what the load than a standard efficiency motor. Power factor and power factor correction. Cost to the suppliers reduce the amount of useful power. It increases transmission and distribution losses, causes large voltage drops in generators, and large exciters are required. The voltage drop of overhead transmission line increases with a decrease in power factor level. That's why you get billed on kVA. The cost to the consumer. It's high electrical cost if charged for a total power amount of kVA, which has been established to be for MOSA's highest cost factor. Low power factor causes poor voltage regulation, resulting in inefficient operation of equipment. If we correct the power factor, it's reactive to current component lags behind the applied voltage by 90 degrees. To avoid over voltage from self-excitation, when a motor and capacitor are switched off, power factor correction should be limited to 0.98. The individual power factor capacitors is only feasible for motors larger than 30 kilowatts. The power factor, or cos phi, is equal to the actual active current divided by the total current. Remember, there's no total corresponding reduction in current in M. Induction motors operating below rated capacity is the main reason for a low power factor. Let's now have a look at the power triangles. So power factor correction before and after example. You can see that the before and after scenarios are illustrated in this slide. Both, for example, let's use electrical motors. Both motors use 80 kilowatts and initially had 60 kVAR and 100 kVA. By reducing the kVAR to 60, we reduce the kVA to 84.2. This is a significant decrease in the kVA. And on this one example, if in Formosa's context, would result in a 4,000 Rand cost reduction. Power factors can be sized by the power factor table. It's a table factor times the real power load in kilowatts. This is important to ensure that power factor is sized correctly. Oversizing these power factor units will result in a longer payback period, and undersizing these units will result in underperformance and the benefits not completely gained. Let's look at the motor power demand. The power demand for a three-phase induction motor formula is displayed in this slide. The energy consumption is also displayed in this slide. The variable factor here is that operating hours is brought into consideration within this formula, where the power formula excludes operating hours and energy consumption formula includes operating hours. Let's look at an energy management opportunity and motor load scheduling. Scheduling motor operations. It needs analysis of plant demand profile, like the profiles pulled up in previous meetings with Formosa Textiles. VCBA is especially susceptible to an opportunity here. To gather more information, we need to determine what exactly VCBA is feeding and drill down on what motors are causing the peak spikes. We need to then smooth out the profile by rescheduling operation periods and lower the overall demand. We can always switch off unproductive motors. The unproductive motors gives a base load to kVA and kilowatts that's unneeded. So for example, if your base load was 10 and you start a motor, you might hit 15 kilowatts. If your base load was 5 and you start up a motor, you might only hit 10 kilowatts. It's very important to make sure that unproductive motors are switched off and started in a scheduled manner, meaning not all motors should be started at once. This also has an impact on the kilowatt hours usage. It's always important to consider the motor drive maintenance alignment. The motor drive maintenance and alignment issues causes a lot of efficiency losses within the system, especially with regards to belt drives, which is evident at the air handling units in the basement of the plant. The drum filters and fans are controlled using belt drive systems that can occur slip as they loosen and lose tension. As can be evident as well, a lot of motors have VSDs in the plant, and that is a better way of controlling the motor speed in order to reduce energy and to achieve desired torque and speed requirements. Remember, to extend the motor life and save the motors, keep an eye on the temperature. The increase in insulation temperature with 10 degrees reduces the motor life by 50%. So ensure enough ventilation for the motors and that they aren't clogged up with any dirt. Make sure that there is no moisture reaching the motors. Run the motors once a week at least for motors standing still in order to ensure that they do not accumulate moisture. Ensure all bearings are greased so that they don't overheat and the heat doesn't transfer back into the motor. An increase in vibration usually means there's losses and misalignment. Motors should not be started more than 3 times an hour. Excessive starting causes heat damage to the motor due to the inrush current heating the motor up. Belt drives and synchronous and V-belts incur energy losses due to flexing and slippage. It can usually save between 2 and 4% by going over to cog or notch to V-belts, or better yet, move over to a VSD. Only if the application allows. For instance, in some regions or in some instances, if a motor jams or if a fan jams or pump, you would rather have the valve burning off than the motor burning out. So if there's a high probability for the motor or for the pump or fan that's being driven by the motor to jam, rather use the cogged or notched V-belts. Keep an eye out for voltage imbalances. The problems occur with voltage imbalances between three-phase loads. The percent voltage imbalance is the ratio of the largest phase voltage difference from average. It's then divided by the average voltage, as displayed in the formula below. For example, if we have a 220, 215 and 210 volts going to a motor, what's a voltage imbalance? At the end, it's 2.3% imbalance. Temperatures and voltages increase in proportion to the square of the voltage imbalance. So a 3% voltage imbalance causes a 9% increase in losses. When looking at single-phase motors, its ultimate in voltage imbalance, dramatic heat rise, so large amperes flowing into the other two phases. Each 10-degree rise reduces a motor life by 50% again. If fused, all three phases should be fused. Overload protection sizes on actual loads rather than the nameplate loads. Phase current increases by square root 3 in single phasing. Remember the temperature increase rule. Power quality issues, especially with regards to harmonics. Power quality is related to how well a bus voltage, usually the facility load bus voltage, maintains a pure sinusoidal waveform at rated voltage and frequency. Power quality issues involve all momentary phenomena including spikes, notches and outages, as well as harmonics and power factor. Modern electronic equipment both causes and is affected by the problem. Power quality is becoming one of the most important issues in energy management today. Let's look at the effects of bad harmonics. You'll have circuit breakers tripping for no reason, neutrals overheating and potential fire hazards, panel or transformers overheating, RFI, radio frequency interference, errors damage in electrical equipment, digital clocks running fast, and failure in power factor correction capacitors. With all the VSDs installed and the spot measurements taken on our harmonics whilst installing the three-phase power meter system, it was noted that the harmonics have issues, and this will be addressed further along the line. In this slide, we can see a voltage variation impact on motor performance. We have starting amps, EFF, power factor, full load amps, starting and maximum torque. We've got the percentage voltage variation versus the percentage changes in motor performance. As you can see, the percent voltage variation translates directly into percentage changes in motor performance and vice versa. So, taking the voltage balance and impact on losses into account, you can see that the percentage phase-to-phase imbalance and the percentage increase in losses and temperature corresponds towards each other. So if we end up, for example, with an 8% phase-to-phase imbalance, we're running at about 80% increases in losses and temperature. That is extremely detrimental to your electrical equipment. So let's look at an energy management opportunity calculation. The power and energy savings depends on the efficiency of standard versus the efficiency of the new motor. So power savings is equal to kilowatts electrical, in other words, kilowatts no load, normal load times load factor divided by efficiency minus the kilowatt normal load factor divided by efficiency, both standard minus energy efficient motors. The energy savings is a power savings calculated above times operating hours. Remember, This is only applicable if your RPMs remain the same. If you achieve higher RPMs with the energy efficient motors, your power consumption goes up. Using a premium efficiency or high efficiency motor will reduce the full load current drawn from the power supply. Therefore, the electrical protection of the motor must be reviewed as well, with overload protection adjusted accordingly. Conversely, the starting current or inrush current, which is normally 4 to 5 times the full load for a standard efficiency motor, will usually increase to 6 to 8 times full load for premium efficiency motors. Again, the motor overload protection system will need to be reviewed to accommodate this factor. In this slide is an energy management opportunity calculations to achieve your annual savings in rands. This calculation can be used whenever motors are replaced